All right, so we have a time evolution operator, u, t naught. And when the Hamiltonian is time independent, then this is just this exponential function. Right, and the idea is that this evolves the system, the state of a system, from t naught to t. Now, the question is going to be, what do we do when we have an exponential with an operator in here? All right, so in general, it's actually complicated. But what we're going to do is we're going to force ourselves to pretty much always be operating with u on a basis of eigenvectors of h itself. So remember what I said before, which was that we can always think of this exponential as the expansion of it. So if I have e to the a, that's equal to 1 plus a plus 1/2 a squared plus 1/6 a cubed, and I'll just write it out as a, and so on. Now, what does this do? So on an arbitrary vector, the a will operate and something will happen. But when it's operating on one of its own eigenvectors, so what do we mean by that? So if we have a solved eigenvalue problem like this, all right, then when we operate with a, we see, every time I see an a, I'm going to get another little a. All right, so let's try that out. E to the a operating on the eigenvector a is just 1 plus a plus a over 2, and so on, operating on a. So we distribute this a in here. We have a plus a on a plus a on a on a, and so on. So we know what this is. This is little a times a, eigenvalue times a. This is going to be little a times a, and that's a number. So this a can move out. So now we have a acting on a again, so we have a squared operating on a. So clearly what that means is we end up with 1 plus a squared over 2, and so on, operating on a. All right, so well, you can do this for any function. So as long as the function can be written in this form, a form of a series of polynomials or a summed series of polynomials, then you can always write it down. So the compact way of writing this is the function of an operator operating on one of its own eigenvectors is going to be the function of the eigenvalue corresponding to that eigenvector times a. And that is why we love the time evolution operator acting in the basis of its own eigenvectors when the Hamiltonian is time independent, as you'll see right now. Okay, because we get to replace the operator with a simple number. Okay, so what we're going to do now is we're going to consider any state, psi of t, and we're going to ask about the expectation value of an operator as a function of time. Okay, this is a very natural thing to do. If operators correspond to things we can measure, then wouldn't you like to know what the expectation value is as a function of time? I would. And a lot of times this is going to correspond to things that are important for spectroscopy. So here's our state. We'll worry about how we get there in just a minute. We're interested in the expectation value of a, and it's going to be presumably some function of time. Maybe, we'll see. Okay, and so this is equal to psi of t, a psi of t. That's the definition, right? Well, now what we can do is we can plug in what we know, or a way to write psi of t, provided we know psi of t naught and the time evolution operator, right? So we're going to plug that in. We're going to plug in u times psi of t0, t naught. Right? And then we're going to plug it in on the left-hand side. Remember how we do? We follow our rules of the Dirac notation. The Ket version will be the adjoint of the Bra version. Right, so we're going to have psi t naught u dagger. U and u dagger are not equal to each other. U is not Hermitian. It is unitary, which means that u dagger is equal to the inverse. It's not equal to u itself. Right, so when we plug this in, we have the expectation value of A, which we predict will be a function of time. It's going to be psi of t naught, u dagger t naught. And of course, what this is just going to mean is that we're going to replace the minus I with plus I. Everything else is the same. All right, but it will be operating to the left. We'll have to think about how we operate from right to left. All right, then we have A. For now, we're assuming that the operator itself, A, does not have any intrinsic time dependence. Right? You can, oops, there's no dagger there. You can, of course, include the case where A did have some time dependence, but here we're not doing that. You know, if you were thinking of the expectation value of position, the position operator doesn't change. Okay, now here is where we pause. Okay, the reason we pause here is because what you see now, I have one formula that simply came from a definition, basically two definitions. I don't even have to say what U is yet. Okay, but I want you to notice that there's two ways to kind of put parentheses here. One way to put parentheses is like this. When I do that, I kind of have the picture that I had before, which is that the state vector has time dependence. And the operator, as I just said, is time independent. That's the way many of you will have already thought about this. But I can put my parentheses in a different way. If I put my parentheses like this, now what happens? The state vectors are time independent. It's just whatever the initial state vector was, but the operator itself, the question I'm asking, becomes time dependent. Well, we have a special name for this. We call this A sub h. And that's U dagger. I'll leave the T's out for now. A, U. All right, so in this case, the operator is time dependent. And the states stay the same. Now, I honestly don't remember from reading the fundamental stuff, like the historical development of this. But the case where the state vectors are time dependent and the operators are not is called the Schrödinger picture. And the word picture is sort of peculiar, but that's what we use here. And the case where the state vectors are time independent and the operators change, you probably can guess, is the Heisenberg. They were sort of like two sides of the coin. Heisenberg picture, right? We will find out there's yet a third picture, which is sort of partially between them, which will be called the interaction picture, and that's the one we will use when we derive the time-dependent perturbation theory. But this, you can see, is a nice anatomy of the time-evolving expectation value of the property A. Okay, so what we're going to do now is we're going to try to make our lives a little bit simple, which is we're going to just consider the case where the state vector, initial time, is actually one of the eigenvectors of the Hamiltonian. Right? Let's call that phi m. Okay, so if it's in a single eigenstate of the Hamiltonian is how some people might say this. I want to know what happens as a function of time when this is the state that you're in. Okay, so let's plug it in. I'm going to start down here. We have A. Okay, we have the time evolution operator. We have the phi m. We have U dagger. We have A. We have U again, but not dagger. All right, so what does this with the right-hand side one do? Okay, the right-hand side one is going to be the exponential operator is operating on one of the eigenvectors of the Hamiltonian. So we'll replace the h with the eigenvalue, which is Em, let's say. Right? We're assuming that we have our solved eigenvalue problem like this. All right, we can do that. The other thing that we're going to have on this side, now we don't necessarily know what it means to operate to the left, so we don't have to know what it means to operate with the left. We can convert this into an operation on the right by taking the adjoint and then taking the adjoint of that again at the end. So let's do that first, because that's sort of the trickier one. All right, so the adjoint of this is going to be u. We know all about u, because we're going to switch the position of the operator and the vector. Okay, and we know that this thing here is equal to this adjoint. Right, now what you see then is I can just calculate this one and then take the adjoint, and I will know what this one is. Okay, so that's what we're going to do. We take this one, which is e to the minus I over h bar. I'm going to replace the h with the eigenvalue. We already know that that's going to happen. T minus T naught on phi m. Okay, so what we see is we've got a convenient number. This is just a number. It's complex, but so what? Complex number multiplied by phi m. And what do we have over here? We have the adjoint. Well, the adjoint of a number is just the complex conjugate of that number. So this a is going to equal this number complex conjugated. I'm going to write out really slow. In the future, we will probably skip a step or two here. But in case this is unfamiliar, I want to make sure everyone knows what's going on. All right, that's the number that we get for this one with the adjoint. We have the phi m. I'm going to move this number over. This is a minus. Notice I put a plus here. I sometimes put pluses just to highlight that they're not minus signs. It helps you see the symmetry or the lack of symmetry. And then we have phi m and phi m. This, of course, is equal to 1 because we picked our basis to be orthonormal. Of course, we didn't pick it to be orthogonal. We picked it to be normalized, though. Well, what's all this? This is the fanciest way in the world, one of the fanciest ways in the world of writing the number 1. Right? You have e to the I plus something, e to the minus plus something, the exact same thing. So that's just equal to 1. It ultimately ends up being e to the 0. And what did I leave out? Of course, I left something out. Let's just erase this. So, of course, the whole point of this was to calculate the expectation value, and I left the operator out. That's very funny. That's okay. We can always remember to put it back in. Here. This is where it goes. You can slide numbers out, and you can move vectors and operators, but they can't move past each other, right? It's like the Tetris blocks. The block can fall down, but it can't go through. You can convert something to an eigenvalue, and that's like taking a line out of your Tetris, and then the whole block can go down again. All right, so here we have that. Now we're going to use lots of notations for these kinds of scalar product of a vector times an operator operating on some other vector. And notice that the two letters are the same here, the two indices are the same. So we're going to call this the matrix element AMM. Why are we calling it a matrix element? Because in practice, you almost always will write down things in the form of a matrix. There's two indices, so when you have two indices, we call that a matrix. And so this is called a matrix element. Good. All right, so we have AMN. So notice that we have AMN, we have a 1. Notice that this does not depend on time. This is a constant value. Right? It's a constant value, which tells you that if you're in one of the eigenstates of the Hamiltonian, If the system is prepared that way, it'll evolve that way. The property A, whatever property it is not going to change. This could be position, won't change. Momentum won't change. All right? And that's we just proved that just now. Now, why is that weird? Let me tell you one reason it's weird. Here is a classical harmonic oscillator. You have a mass on a spring. You have a displacement x from the equilibrium position. If you pull the spring, it's at rest, and you let go of it, you know what's going to happen. You've probably done the experiment. You pull it to positive x, it's going to oscillate like this. The amplitude of the oscillation, or the x position, let's call it, since I've already just defined it that way. The position x will vary as a function of time. The magnitude here will be like the amplitude. You know that you can pull this the least little amount. And then you can pull it a little bit more, and you can pull it a little bit more. And the energy of the wave is going to be proportional to the intensity, or the square of this displacement. If you integrate over a cycle, for example. So if you integrate the intensity over a cycle. So in the idea is that this thing oscillates back and forth. The kinetic energy is controlled by how far you pull it out. The potential energy too. The total energy is. Thus the sum of those two. And it's arbitrary. You can make it whatever you want. But it's certainly intuitive to think, oh, if I have a harmonic oscillator, some kind of oscillator, it doesn't even have to be a harmonic, and it's at rest, it's at its equilibrium position, it's not moving. Fine. But then if I excite it by adding energy to it, it should move. Super obvious, right? Well, what did we just find out about a quantum mechanical harmonic oscillator? Now, it could be anything, but the harmonic oscillator is going to have the strongest intuitive connection, I think, to most people. Here is the potential energy function of a harmonic oscillator. It's the same as this one. It's a quadratic function. We can define everything exactly the same. And it's very informative to consider the comparison between classical and quantum oscillators. Well, one thing that we know from quantum mechanics of a harmonic oscillator is that the energy levels are discrete. Right? They're n plus a half times a constant, h bar omega. And omega is related to the spring constant. These energy levels are here, and they're evenly spaced, or equally spaced. That's the hallmark signature of a harmonic oscillator. They start at 0, 1, 2, and so on. So what do you notice? First, it's totally symmetrical. The potential energy is totally symmetrical. It's just a quadratic function. The wave functions, or the eigenfunctions of the Hamiltonian, are a Gaussian function times a polynomial and some normalization factor. That's the least important thing. But the Gaussian function times the Hermite polynomial, gives you all these wave functions. So you'll have something that looks like that, something that looks like this, and so on. They're all symmetrical. They have different signs. But if you square them, which is what matters, you'll see that they are symmetrical functions. So the probability of finding, or the expectation value of position, is always 0. 0 is in the middle, right? For each of the eigenstates. That's what AMM would be. If A is X, MM means the expectation value of X, provided you're in the state M, whatever that happens to be. So if M is 0, it'll be whatever the probability is, or the expectation value of X to be in the 0 state, right? The ground state. Well, no one would freak out if you said the ground state particle is in the middle and it doesn't move. That's like the classical oscillator being at rest. But now if you go put in this amount of energy, which, if it was a vibration in a molecule, it could be thousands of wave numbers, much, much bigger than kT. And what do you find? If you actually produce a molecule or one of these vibrations in the excited state, and it's there, it'll have the value of the expectation value of X will have the value for that eigenfunction or eigenvector. And it will be 0 too. and it won't change. So what that tells you is a vibrationally excited harmonic oscillator doesn't oscillate. That should be surprising if you haven't thought about that before. So then what makes things move? What makes it oscillate? How do I get the vibrational motion that I've been talking about with my friends for all this time? One of the first things people talk about, when they learn about thermodynamics, for example, they get all excited about absolute zero. They'll say things like, oh, at absolute zero, all the vibrational motion ceases, right? We have other, a little bit more rigorous definitions of what absolute zero means. And for many systems, the vibrational energy ceases long before you reach absolute zero. For example, an OH stretch in water has zero probability, practically speaking, of being in an excited vibrational state at room temperature. 3,500 wave numbers. Imagine how hot you'd have to get to have an appreciable population in the excited state. But then even if it was not, it was just a population, still wouldn't be oscillating. Obviously, this is a little bit like a paradox. It's not really a paradox, but it seems a little bit like a paradox. That means I'm leaving something out. Two things I'm leaving out. One is that this is just the way it is. Right? If you're in a state of the Hamiltonian, you are stationary. There's no time evolution that you could observe. The phase will evolve, and that's it. The other thing is, in real life, we don't actually have unitary evolution. All right? So if I excite a vibration, it's going to relax to the ground state eventually. That's not included in this. We're going to have to figure out how to put that in. But nevertheless, even with that, you wouldn't see coherent oscillation or vibrational motion the way you think of it, unless you have a superposition of two states. And that is key. The motion, the way we think of it classically, arises from the superpositions of quantum states. That is kind of weird. You do something that some people think is weird. Schrödinger's cat. Oh my gosh, the cat's in a superposition of alive and dead. But then it turns out it's purring. See that? The cat's not going to purr if it's not in a superposition of anything, because that's motion. It's a vocal cord vibrating back and forth. So we need to get our heads around superposition and what does it really mean? It means a couple of different things, but the thing it means for spectroscopy is it means that there's going to be some time dependence to operators, to their expectation values. The one we care about the most is this one, the dipole moment. Because the dipole moment, if it evolves, the expectation value of it, then this is what we call a polarization. And this can emit a field. And that's the basis of most spectroscopy. Now, of course, you could always say, what about Raman spectroscopy? Well, you can make something that acts just like this. By using the polarizability and a field, it makes a dipole moment as well. Right? So this is very general. Okay, so that will stop. We'll stop here.